All right, here we go. So you should have picked up a notes packet when you came in today. Also, don't forget that your what's this, salmon colored worksheet? This due today. Make sure you turn that in today. Otherwise, if you turn it in tomorrow, it's not worth anything. Okay? Right?
I mean, I'm just go get it. I'm not that.
I just got it.
What?
I just got it.
So it should be done. You
It
do it
is.
today.
Yeah.
Then what are you
I
worried
didn't know
about?
I was doing that.
Yeah, said so yesterday.
I wasn't there.
Okay, so we got that. Launcher labs. Those are the green packets that most of you finished yesterday in class. Those are due on Friday. For those of you that didn't finish those yet, those due Friday. NTC final exam is going to be on May 16th and May 17th. We're going to give it to you, and we're going to let you go, and we're going to get 6 months to get it done in. Okay? All right? And then after those 6 months, it's done. Okay? All right? So we got that going on. We are going to start this next. We have 2 units to go. Okay? We have 2 units to get done yet, and review for the final, and get all this stuff done in the next 13 days, which really is 11 days because we don't have classes on Monday. So with 11 days, we got 2 units to go. Luckily, they're nice, short, easy type units, things that you've already kind of seen a little bit of. Okay? Okay? So just when you have all the answers, I'm going to go back and I'm going to change the questions. Okay? So, for instance, we're going to be talking today complex numbers, and then we're going to be talking polar numbers is going to be the next one. They kind of run together. Okay? So a complex number is made up of a number with 2 parts. Okay? So the 2 parts are, you've got the real part. Come on now. And you've got the imaginary part. We also have a brand new coordinate system. Meaning, instead of like the x-axis and the y-axis, okay, that's called the Cartesian coordinate system. We now have a new coordinate system, which also allows me to explain the joke, ha ha he he. Okay, the new coordinate system has the real axis is the old x-axis. Okay? So the imaginary axis has the real part there, or the complex axis, or the complex coordinate system. And then it has the imaginary as the old y. Okay? So real is horizontal, imaginary is vertical. So when Mama 8I up here is saying, get back up here before one of you loses an eye. Okay, that's the vertical axis, the I-axis. Okay, all right. So that then, that then allows us to, instead of writing this complex number all the time as A plus BI, we can write it just as A comma B in the complex plane, where A then is the real part and B is the imaginary part. That's when we switch over to the complex part. Today, what we're going to talk about is we're going to talk about the trig form of a complex number. Now, you've seen a lot of this stuff already, so we can figure out how to find x's, or excuse me, a's and b's. So let's make our point or our complex number be -2 minus 5i. In terms of the point in the complex plane, that would be the point 2, comma, -5. Do we all agree with that? That is the point in the complex plane. Real, comma, imaginary. If I were to sketch said point, well, that would be 2 over and 5 down. So that would be this point right there. Where now this is the real, and this is the imaginary. Now, if I bring trig into it, I could get here an angle, which we would call theta, and I can get a distance away from the center, the origin, if you will, as r. So each and every complex number is a certain distance from the origin. We call that r, and on a directed ray with angle theta. So, because we're in the complex plane, or because we're using trig, we can find r and theta very easily. And you've done it already. R is going to be the square root of a squared plus b squared. That's what r was back in parametrics, right? Or in fact, excuse me, not parametrics. One too many units, or not enough units. One too few units. Back in vectors, r was square root of a squared, or in that case, it was x squared plus y. Okay. How can we find theta? Seen that before, haven't you? Okay. That gives us our reference angle, and then depending upon where we're at, if we're in quadrant number 1, then theta is our reference angle. If we're in quadrant number 2, theta is 180 minus our reference angle. If we're in quadrant number 3, then theta is 180 plus our reference angle. And if we're in quadrant number 4, then theta is 360 degrees minus our reference angle. All stuff you've seen before. Okay? We're just applying it now to a different place. So now we're back in this. Okay? So same problem here now, as we just did before. It's in the same spot. How do we write the complex number in trig form? Well, the trig form, and this is kind of important, you should put a couple of stars around this. The trig form of a complex number is r times the cosine of theta plus I times the sine of theta. So in this particular case, just want to make sure that we're not doing it later on. Okay. So in this particular case, where we've got that, my R value is going to be the square root of 2 squared plus negative 5 squared. 2 squared is 4, negative 5 squared is 25 plus 4 is 29. So this is, our value here is the square root of 29. Okay? Theta prime then is going to be the inverse tangent of 5/2. What is the inverse tangent of 5/2? Inverse tangent any one of 5/2 in degrees. Calculators might be in radians, just so you know. Anyone, inverse tangent 5/2. Should have had it by now. What do you got? 68 point, yep, I would go 0.20 degrees there. Which quadrant is this complex number in? It's in quadrant 4. So we take 360 and we subtract off that answer. So actual theta is 291.80 degrees. Yes? So the trig form of this complex number would be z here equals the square root of 29 times the cosine of 291.80 degrees plus I times the sine of 291.80 degrees. Except you would, I hopefully write it all in one line, as opposed to me who had to move this over, and then I gotta go here and here, and then plus like that, much better. So that then gives us 3 different ways to represent the same complex number. Okay? So we have what's called the standard form. Standard form of a complex number is A plus BI. That's the same as the ordered pair form. Which would be A comma B. That's the same as the trig form, which is going to be R times the cosine of theta plus I sine of theta. Or, because that's a lot of writing, that's a lot of extra writing all the time, what we mathematicians have also done here is we call that R CIS theta. CIS stands for cosine plus I sine. So you don't have to write that out every single time. Repeat the angles every time. You can just write it as CIS. Okay? Let's do this. Let's get some practice in here. We want to represent Z in trig form. Okay? So first off, let's go. So this is standard form, right, of number 1. Let's put it in ordered pair form. So this would be the same as what would my ordered pair be? -3, 4 is what I kind of heard somebody mumble. Yes? Okay? All right? Find me R. Did you get 5? By now, you shouldn't have even had to use the calculator for that one. You should know 3, 4, 5, and 6. All right? Now we need to find theta. What we got for a reference angle? Which quadrant is this complex number in? The 2. So how do I find actual theta? Oops, I put theta prime. Actual theta is 180 minus theta prime. So actual theta is 126.87. That. So the complex number here in trig form would be, and I'm going to write it in the shortened form. So it would be 5 CIS 126.87 degrees. Which would be the same as see how the shortcut's much easier. That's why we mathematicians came up with CIS is much easier. Yep. You do number 2. So this one would be the point -2, -2 square roots of 3. My R value would be -2 squared plus -2 square roots of 3 squared. Then take the square root of that. This one's 4. This one's 12. So that's going to be the square root of 16, which is 4. Then my inverse tangent of 2 square roots of 3 all over 2, which is going to be 60 degrees. This is in quadrant 3. So theta is 180 plus my reference angle, which is 240 degrees. So this one would be 4 CIS 240 degrees. Now, way back in geometry, back when you were a tree, you actually learned that if you have a right triangle and it was -2 there, -2 square roots of 3 there, and it was a right triangle, that if you had this relationship, this 30, 60, 90 relationship, where if you had this side, we'll call it x, then this side was going to be x square roots of 3, then this side was going to be 2x. So you could have seen that that was a special right triangle and done that. Now, I don't expect you to remember that. That's why I showed it the other way first, the long way first. If you remember the shortcut, more power to you. More power to you. All right? What about number 3 here? Z equals 8i. What would the ordered pair form of this one be? 0, 8. Yeah. Okay. So, without doing any math, how far away is that point from the origin? 8, because it's on the imaginary axis. So my R value is 8. Without doing any math, what's the theta angle? Why 90? Because it's straight up, right? And straight up on the unit circle is 90. So this one is 8 CIS 90 degrees. Okay. Do number 4. I did mine special right triangle way because it's faster. If you would have done square root of a squared plus b squared, you still would have gotten 10. If you would have done inverse sine, or inverse tangent, you would have gotten 30. It's in quadrant 3, so you would have to add 180 to it. So you get 210. Questions on that one? Okay. You should have, tap the brakes down here. Maybe not. On yours, do numbers 5 and 6 now on your own. and then we'll check them tomorrow when you come to class at the start of class.